Okay, in this class we will look at generative adversarial networks. Remember what the story was. So, we have uh, a random variable that we are sampling from. Let us assume that we are sampling from normal distribution, because typically what happens is that the data that we get will mostly have infinite support. So, we do not want to start from a uniform random variable that has finite support. We would like to start from a random variable that has infinite support. So, typically in all these generative models, the z, which is the random variable that is being transformed, is taken to be normally distributed, not uniform, okay, because we assume that we also know how to sample from normal distribution, because we know the deterministic transformation. Okay. So, then we have to learn the underlying function. So, this goes as an input to a neural network now, and this neural network is that function that I was talking about, which will give you samples from correct. So, this is any neural network. So, you take a neural network, and the reason I have drawn this neural network this way is that I said z is always in Rk, which is less than k is less than d. Therefore, you need to increase the dimensions of this neural network, right, because you need to get to the d dimensions from k dimensions. That is why the shape. Okay. Now, this is a neural network. So, now what do we have to do? We will have to ensure that this p theta of x is close to px in distribution. How do we do that? We minimize a divergence metric, right. Now, in this generative adversarial network, the underlying divergence metric that gets minimized is what is called as an F divergence, specifically one specific form of this F divergence called the Jensen-Shannon divergence. Now, why would that how would you minimize that F divergence function or a Jensen-Shannon divergence is a matter of detail, meaning, as I said, I will do it in the next course. What will happen algorithmically is what I will show. So, what we should do right now is get this theta, okay, that would minimize some divergence metric, okay, which is typically what is called as the F divergence between Px and P theta. Now, KL divergence also happens to be a special case of the F divergence. F divergence will give you a family of infinite divergence metrics, of which KL, reverse forward reverse KL, Jensen-Shannon, chi-squared, everything becomes a special member of this family. Okay. Now, how do you solve this optimization problem? Remember that we cannot compute this KL divergence because we do not know what Px is, correct. Do we know what P theta is? We do not know what P theta is. However, we can get samples from P theta. How? I mean, do a forward pass through this neural network, you get samples from P theta. You get samples from P theta, right. So, we have now the question is, given that we have samples from Px and samples from P theta, estimate this divergence metric. It turns out that this divergence metric is not tractable, it cannot be computed. So, what did we do in the variational methods in the EM method? We constructed bounds on the divergence metric, which is the evidence lower bound, and instead of optimizing the actual divergence metric, we optimize a bound on it. Exact same technique occurs here. So, here is the outline of how the entire math works out. I will not do the math in this course, but the math works out that when you construct a bound on this F divergence, the bound will take a form where there will be linear combination of two expectations, and these two expectations are taken over P theta and Px respectively. So, what will happen is this divergence metric, right, the bound on this divergence metric will have a form where you will have an expectation of some function over Px plus an expectation of another function over P theta, okay, and these two functions can be computable, okay. There will be some computing functions that can be computed, and there are expectations over Px and P theta. What is this? This is the bound that we compute on the divergence metric that we would want to minimize. You get what I am saying? Now, these expectations can be estimated using samples. Why? Law of large numbers. You invoke law of large numbers and say that look, these expectations now can be estimated because I have samples from Px, I have samples from P theta, that is it, and this becomes the loss function for the so called loss function for the entire generative model. That is how the math works out to be. I will not do that, I will just write down this so called loss function and tell you how to do it algorithmically, because it is a part of your third assignment. Did you get what is happening? So, the principle is that we will minimize the divergence metric. Okay, we cannot minimize the divergence metric because of the intractability of Px and P theta. We construct a bound which is the variational bound, okay, and that bound finally turns out to be a sum of expectations, two expectations, where the first expectation is with respect to the true distribution and the second expectation is with respect to the generated distribution as it is called. Some people also call this the true distribution and the fake distribution and so on, right. So, true data, fake data or whatever, okay. Is it okay? So, now maybe I should have written this. This is, I think, log of what's the exact form? Is it? I think this is how it will turn out to be. Just give me a second, I will come. See, the point is, I will tell you why this is not of importance. I told you that there is a family of divergence metrics, right. Depending upon what family of divergence metric that you choose, the functional form of these things inside the expectation changes, right. In fact, I can choose a divergence metric that would give this to be exactly of this form, okay, but there is one particular divergence metric that is called the generative adversarial network, which will go to this. I think this is log of d, and let me just confirm this once. Log of 1 minus this, yeah. I think this is that case where you make an approximation so that the underlying mode collapse problem will go away. I think that is not what we are looking at. The naive thing will be log of 1 minus d phi of x cap. Okay. Now, okay, what is this loss function is? Please remember that this loss function is the bound on the divergence metric that we would want to optimize. And how do we go from here to here is in the initial lecture of the next course, okay. But take it for granted that we construct a bound on this divergence metric and we end up getting this sort of a thing. Now, here we know what x is, x is our data points and we know how to compute this expectation. What is x cap? X cap is the output of this neural network G, that also we know. What is this D? Right, there is this function D, okay. So, now this D is another neural network that we construct here, okay. Where does this D come from? See, this D comes up when we construct the lower bound on the divergence metric, okay. Here is how it happens. Now, the lower bound that we construct on this, okay, let me actually do the math, I think a little bit of math so that it is complete. Okay. Now what we want to do is minimize this, right? Theta star is minimize this divergence metric. Okay, we cannot minimize this divergence metric. What will happen is this will become an approximate optimization over theta, and we construct a bound on this, some okay. Now this bound on df, need to keep pushing this. This bound on df itself will be an optimization problem, okay, over what happens is there is a function that you are trying to optimize. So please pay attention here, because I am only giving you the sketch of the math and not doing the entire math. So there is a function that you are trying to optimize, correct, and we cannot optimize that function with respect to the particular parameters because of intractability. What we do is we construct a bound, okay, on that objective function that we are optimizing. That bound that we construct, okay, itself involves an optimization problem over another class of functions. Do you see what I am saying? So df is the function that we are trying to optimize, we cannot optimize that. So we construct a bound on df. Now this bound on df consists of another optimization problem over another class of functions. You see what I am saying? Do you understand? Now these class of functions are what are approximated using another neural network here. So should I tell you the thing again? So there is a function that there is an objective function that we are trying to optimize with respect to one set of parameters, okay. We cannot optimize that, and that is why we construct a bound on top of it, right. And while constructing that bound, we will have to solve another optimization problem with respect to another set of functions. That is what I have written as this max over L of theta comma phi. Now it is like this: first you solve this inner optimization problem to construct the bound, and once you construct the bound, you minimize that with respect to another set of variables theta, that is it. Do you see? So these are again saddle point problems. These sort of problems are called saddle point optimization problems, where there is one objective function and there are two optimization variables. So you are seeking the extremum point of that objective function, which is maximized with respect to one set of parameters, at the exact same point minimizes with respect to other set of parameters. That is why it is called a saddle. Typically in an optimization problem you avoid saddle points, but here is an optimization problem where you deliberately seek saddle points, because that is how the problem is constructed. That is why training GANs is hard. You might have heard that training GANs. So today generative adversarial networks is not the state of the art model for generation, is because of this, that you are deliberately seeking for a saddle point, which is a hard problem to solve in higher dimensions.
Are we using dedication for it? Because
we are using the same SGD, Adam, etc. to solve this. I'll come to that in a while, right. Now please understand how this problem is constructed first, right. So the goal is to sample from the underlying distribution, okay, and the principle is to find the parameters of this g function such that the divergence metric is minimized. We cannot minimize this divergence metric, therefore we construct a bound on it, and while we construct that bound, the bound itself becomes solution to another optimization problem which involves another class of functions, right. And that is why the final problem that we would solve is we seek phi star and theta star, okay, that are optima of this particular function. Now what is this phi? Where is this phi coming from? So what is this theta? Theta is the parameters of that function which would map the Gaussian random variable to random variable of interest, and therefore it is also called a generator. Generator function is the one that transforms the arbitrary random variable to random variable of interest, right. Where is this phi coming from? So, this phi are the parameters of those set of functions, okay, that would define the bound on the divergence metric that we are trying to optimize. Understood? Any questions on this? Yeah. It's not a latent variable, right, because it's the parameters of another set of functions. It's not a latent variable. So, typically latent variable is a variable that is not observed, right, in the random variable itself, in the space of sample space itself. That's an additional random variable that you introduce. Here it's a function. So, phi are the parameters of class of functions that you would try to optimize.
What are these functions?
What do you mean by what are these functions?
As in, do we have some assumption about their functional form?
Yes, depends upon what divergence metric that you use. Typically algorithmically what is done is, this is approximated using another neural network, okay. What is to be controlled is, you have to control the output of this particular function. How do you control the output of a neural network? How do you control the output of a, suppose you want a neural network to give numbers between 0 and 1, what do you do? Huh? No. You want your neural network to output a number between 0 and 1, what do you do? Activations, right? Choose your activations appropriately, that is it. Have a neural network, choose its outermost layer appropriately. And what does that output layer depend upon? It depends upon what is the divergence measure that you are choosing, that is it. Okay, hold on. For one particular divergence measure called the Jensen-Shannon divergence, this function d, right, or this function that we are talking about, has the range between 0 and 1 for this one particular divergence metric that we choose, which I will show one particular instantiation of this entire class of models. But I want you to understand how did we arrive at this particular type of saddle point objective function, that is it. Okay, we will spend some time on it. Please tell me if you understood the underlying principles of how did we arrive at this. Let me repeat again, shall I? What did we do? I hope that you understand this construct, right? How did we get this construct? This you understand, right? Now we want to get the parameters theta, okay, in such a way that a particular divergence metric is minimized, and while we are optimizing the divergence metric, we want to compute this divergence, which we cannot, okay. You have to take my word for it, we cannot compute this divergence metric. And what is the mathematical workaround? The mathematical workaround is to construct a bound on this divergence metric. While we construct that bound on the divergence metric, this bound itself involves solving another optimization problem with respect to another set of functions, and those set of functions we define using another parametric family of functions called d phi. So, solving or rather getting a sampler now is equivalent to solving this inner optimization problem to get the bound on the divergence metric. Once you solve that, you solve the outer optimization problem that would minimize the divergence between Px and P theta, that is it. Questions on this? Yeah.
Calculate the bound on df, that itself doesn't know p exists or not, right? We are just considering on the data. Like p is a construct that we introduce externally.
What did we introduce?
That's
Phi. Okay. That's correct.
Yeah. So it feels like phi is kind of a latent variable that is assumed in the structure itself, because it is.
Oh, you want to justify your previous comments. Okay. See, it's in literature it is called, it is not a latent variable because it is the parameter of the model. See, model parameters are definitely latent. So, you take a neural network. Do you want to call the parameters of a neural network latent variable? Typically in a non-Bayesian setting, you do not want to treat your parameters as random variables, unless you take Bayesian neural networks kind of setting where you make your parameters themselves random variables, right. In the non-parametric cases or non-Bayesian cases, you do not want to call your neural network itself, parameters of neural networks are a latent variable, right. If you are saying that okay, it is an unknown information that we are introducing to the model, of course, sure, but do not call it a latent variable because that has a different connotation, that is it. Okay.
Phi is a like inherent information that is already present in the TF.
Do not call it a latent variable, it is what you are saying, yes, it is something that will give you the bound, that is it. You had another question, I suppose, yeah.
So, do we solve the optimization problem to tighten the bound?
Yes, that is correct, yes. So, this the inner optimum, in fact we will show that there, we will show the existence proof also, we will show that there exists a particular D, okay, for which the inner bound will become tight.
And is it somewhat similar to the EM case where we do not have a
It is similar to the EM case, but in the EM case the bound does not depend on solving another, so the bound does not involve solving another optimization problem.
if we didn't know Q, like in GMF we know Q.
Yes, yes, if we do not know Q, we will do what is called as variational inference, which is VAE, which is, even that does not involve solving an inner optimization problem, that is how they are different. It is a good observation by the way, yeah. It is similar to EM in the sense that you cannot solve the divergence metric, construct a bound and solve it, but the bound, construction of bound itself involves an optimization problem here, which is not the case with EM, that is it. Anything else? Yeah.
Unlike the case where we had a one-to-one mapping of the p theta function with whatever loss function we define, here we do not have a form for it. Like whichever parametric form of the distribution with p theta we have.
We are not making any parametric assumption here, right? So this is implicit. P theta is implicitly coming from G. Whatever function that this neural network imposes is what our P theta is. We do not even know what P theta is, right? That is why I call it an implicit generative model, because all you are learning is to sample without even knowing what P theta is. You are implicitly estimating Px, not explicitly. Yeah.
So regarding the loss function, what exactly is it measuring? Because we look at other loss functions like MSC and MAE, it's like measuring the distance.
See, here it is measuring the divergence between two distributions, that is it. That is it. See, even MSCMA are that, no?
But MSC and MAE we given 2 points, say like X.
No. MSC, see, you start from a probabilistic standpoint, it is still KL divergence. See, KL divergence under certain distributional assumptions boil down to MSCMA, that is it, right. But if you want a deterministic way of looking at this loss function as well, I will give you one hand wavy explanation that is seen everywhere in blog posts when they describe what GAN is. Okay, I will talk about that as well, but from a probabilistic standpoint, remember what is happening, we are still minimizing the divergence metric, in this case a bound on it, right. Okay, anything else? Yeah.
This p theta is coming from G theta implicitly.
Correct.
Let us say G theta is a neural network, and so p theta means the ERM and the underlying distribution. Is it the same or it's?
No, you are asking what P theta is. P theta is whatever neural network imposes, that is it. Yeah. You do not know what that is, but you want that to be closer to Px, that is it.
And for EM algorithm or probabilistic approach that we see in the discriminator models, we have used the KL divergence there.
We are using some other divergence here.
So why we choose KL there?
I see. See, there are, every divergence metric has a particular property. Now, for instance, KL divergence has this property that it is not symmetric. So that translates to some degenerative properties in generative modeling. So for instance, if you want the details, right, what happens is KL will ensure that you will cover the support of the underlying distribution, but it will not ensure that the model is not sampling from the part that is outside of the support of the distribution, right. And reverse KL has a reverse behavior, and we want some balance between those two, and that is why we choose a other divergence metric. Okay, so now we will see what happens algorithmically. So what, in one particular case, right, if the F divergence is chosen to be this particular divergence called Jensen-Shannon divergence, see L theta comma phi will take this particular form. Yeah, for this particular case of the divergence metric, L theta phi will take this particular form. Okay. Now, where do you see theta in this loss function? It has to depend both on theta and phi, right? Where is the dependence on theta here? Huh? X cap, right? X cap is g theta of z, right? That is why it's dependent on. So here x cap is g theta of z. Okay. Now let us look at how this is done in an algorithmic way. So now what happens is, given the data set D, you want to write it down. Okay. I will write again, perhaps, no problem. See, this Z is sampled from normal 0 1. We have this neural network which is called the generator neural network, g theta of z, you are getting x cap here, and we have another neural network. This neural network is the one that is used to construct the bound, right. So it will take x and x cap both as input, and it will give a value between 0 and 1 for this particular divergence metric. If it is for a different particular divergence metric, the output of this particular neural network will be different. So typically this neural network is called the generator neural network, and this neural network is called the critique neural network. Critique or discriminator, some people call it critique, some people call it discriminator. Okay. So let us write down the loss function. So what we want is, we are seeking theta star and phi star that would minimize and maximize this particular loss function simultaneously, right, or alternatively. It is a saddle point problem that we are solving. L is equal to the expectation of log of d phi computed at x, where x is coming from px, plus expectation of, what was it, log of 1 minus d that is computed at x cap, or let me write it as g theta of z, and this expectation is taken over x cap coming from p theta. This is the loss function, right. Now how do we solve this, how do we construct this algorithmically as follows, right. So take a batch of data, okay, sample a few points from z and pass it through g theta. What do you get? You get some points of x cap. So now you have some points of x, which is data, a few points of x cap, that is generated data. Okay. Now to compute this expectation, how is this expectation computed? You can approximate this by 1 by n, I is 1 through n, so log of d phi of xi, correct. This is how we approximate this using invoke the law of large numbers, and similarly for the next term as well. Now what one should do is take a batch of data, the input data, and generate a few samples of x cap. So now you have a few samples of x and few samples of x cap. How do you generate, how do you get a few samples of x cap? By doing a forward pass through generator, okay, with the current theta. Okay. Then pass all those samples of x through the critic. What do you get? You compute d phi of x. Do you see this? Okay. Then take all those x caps and pass it through the same critique and compute d phi of g theta of z, or d phi of x cap. Now we have both the terms that we need. Compute them here and then do one backward pass through d phi and update phi. That is one pass through discriminator. Do you understand? Now then you have to solve the optimization problem on generator, and by the way, for discriminator you will have to take the negative of this and then optimize, no, because you are solving the maximization problem here, right. Then to optimize for the generator, what do you have to do? Take some samples of x, pass it to the discriminator, okay, compute this particular first term. Actually, for the generator you do not have to compute this first term because the first term is independent of theta. You only take some points of z and pass it through the generator, get your x cap, pass it through the discriminator, find this compute this term and back propagate all the way from discriminator to the generator by keeping phi a constant. That is it. That is one backward pass through generator and keep doing this alternatively. That is GAN training.
So we
Let me, do you have to repeat or did you understand? It is only 2 loss terms and 2 neural networks, right. So, compute the appropriate loss terms, do forward pass and backward pass appropriately, that is it. Of course, I mean this is simply gradient descent.
we optimize both variables simultaneously.
No, when you are optimizing for phi, keep theta constant. When you are optimizing for theta, keep phi. It is an alternate optimization.
That we didn't looking as a saddle point as a directly because we are optimizing one at a time. Right?
Saddle point, right? Given one particular set of parameters, you are looking for the saddle for the other thing, and your alternative.
Saying is that because there is a paper gradient descent for just do the minimizers almost surely.
That is for only convex cases. We are not even close to convex cases here. None of the problems that we solve in machine learning are convex. So, all the results that we have for convexity of gradient descent does not apply here at all. Did you get how to train this? Yeah.
How do we choose X?
Batch wise sampling, no, we have data. Just take one batch of data.
We to generate X cap, we take different sets.
Yes. So, if you take a batch size of 32, you take 32 data points from the input data set and generate 32 Z's and generate them, and you do one pass through both discriminator and generator, okay, and then you do one epoch, you do multiple epochs on the entire data, just like you train any other neural network, you do this. Is it okay?
We can train them simultaneously.
It is actually tried simultaneously. You train generator, solve this inner optimization problem by keeping phi a constant and then train that and do it alternatively. In fact, the ratio is not 1:1. Typically you train the generator more and discriminator less, it or the other way around depending upon what your model is and so on, that is it.
Like X1 and X1 cap,
They
don't have to be related.
Absolutely not, they are not related because everything we are doing at the distributional level, not at a sample level at all, okay. Now once you do this, once you train this, how do you use it during inference? During inference you discard the critique completely. You take z and pass it through g theta. If you have done it properly, then the samples that you get at the output of the g theta has to be the samples from px. That is what this person does not exist does. It has actually trained a GAN, and this is there in your assignment. When I trained my first GAN, right, in 2016-15 times, it was amazing to look at those new non-existent pictures being generated. Is that all right? Now, to answer your question, right, what does this actually mean from a deterministic? I could have talked about this GAN completely without even talking about distributional minimization from this angle. I will tell you how. So, look at what is this doing. See, think of this discriminator. See, what is this discriminator? It is taking x and x cap as input and giving you a number between 0 and 1. Anything that gives you a number between 0 and 1 can be interpreted as a classifier, or rather this discriminator is giving you a probability, okay. Now log of d phi of x is what? It is the probability of, and this expectation is with respect to px. So this is nothing but the entropy, negative of the entropy of the random variable that will give you the probability of this particular x coming from the true data. So this d phi of x, you interpret this, when does this d phi of x will maximize? If it gives 1, it will get maximized. Right? When would it give 1? When it is coming from the true data. If it is coming from true data, then this is maximizing, okay. And what is this? What is 1 minus d phi of, what is d phi of x cap? D phi of x cap is the probability that x cap is coming from the generated data. What is 1 minus that? It is probability that it is not coming from it. I want to maximize that. So these two terms are saying that this discriminator now has to maximize the probability of x coming from true data and x cap not coming from true data. So, this discriminator has to become a good critique, a good classifier, right. And what is this generator trying to do? It is trying to minimize the exact same loss function, which is saying that make this classifier not a good classifier, make this classifier fail. Now, when would this classifier, so what is this classifying between? What is this discriminator trying to classify between? It is trying to classify between px, the samples of px and samples of p theta. When would the classification becomes difficult? If px and p theta become the exact same distribution. That is what this generator is trying to do. So, as they say, this generator is trying to fool the discriminator and vice versa. So, that is why the name adversaries. So, this generator and discriminator, see, any saddle point optimization problem is an adversarial optimization problem, because you have an objective function and two different set of parameters that are trying to optimize it in two different directions. Okay. So, if you want a folklore way of looking at it, it is that, okay, this discriminator is trying to fool the generator and the generator is trying to fool the discriminator and so on, because this loss function can be seen as maximizing the probability that this discriminator is trying to find out whether the data is coming from the true distribution or the so called fake or generated distribution, and this generator is trying to undo what this discriminator is trying to do, which is, when would this classifier, it is like this, no, people tell you this story that, oh, look at this, this x cap is coming. So, this discriminator is trying to see whether this x cap is coming from true data or not. As long as this can successfully discriminate between true data and the fake data, then this generator is not generating properly. The moment it stops becoming a good critique, then you have fooled this thing enough so that you are generating from the true distribution is the story, and they write this loss function saying that this is the thing that would maximize the probability of discriminating, maximizing the probability that it comes from true data, this not coming from true data, then you maximize this, and then you write a minimization saying that that would because the generator wants to undo what the discriminator is doing. If discriminator is maximizing a loss function, then the generator has to minimize that loss function, and that is why you have a min max problem here, is how people present it. I am not a big fan of that at all. I mean, it all looks like a hand wavy story. What is actually happening is this, right? You start from minimizing a divergence metric, construct a bound on it. The bound involves another optimization problem, which is parameterized using another neural network. See, this discriminator story comes as a consequence of solving this nice mathematical construct. You should not begin from it. Right? That is my way of looking at things. Anyway, you understood that this is what a GAN is, right? Generative Adversarial Networks, right? Where the idea is, let me summarize what we did today. Generative models are samplers. We are still estimating the underlying distribution. So, how do we do that? Start from an arbitrary random variable that we know how to sample from and pass it through a discriminative function whose parameters are learnable. Now, the idea is to set the parameters of this deterministic function, which is a neural network in our case, in such a way that a divergence metric between the true distribution and the distribution that this deterministic function is imposing on the underlying arbitrary random variable is minimized. Okay. This is the principle that is behind all generative models, be it a GAN or a VAE or LLMs, everything. So, we will see different ways of solving this problem. In what is called as generative adversarial networks, what we do is we choose this family of divergence metrics called F divergences. And if we choose F divergences, then minimizing that divergence minimization becomes intractable, and therefore we construct bounds on it. While constructing the bound, to construct the bound, we will have to solve another optimization problem that involves a class of functions, okay, that is again approximated using another set of neural networks. Okay. Now, you first construct the bound by solving an optimization problem, and once you construct that bound, you minimize the divergence metric, the bound on the divergence metric. So, that involves solving two optimization problems on the same objective function, and the inner optimization problem becomes a maximization by construction and the outer one becomes minimization, and that is why you end up getting a saddle point problem, which is also called an adversarial optimization. Okay, this is the general principle of what is called as F divergence minimizers. So, they are called variational divergence minimizers. That is how I introduce this topic in the next course. A special case of it is what is called as a generative adversarial network, where the chosen F divergence is Jensen-Shannon divergence, and if you choose that particular divergence as the divergence metric, the underlying bound on the objective function or the divergence metric will take this particular form, which can be interpreted as a classifier. And we saw how to optimize this, right? There is one pass through the generator, you compute the loss function, and just the exact same gradient descent methods that we were using, we will use that. Post training, you discard the discriminator completely. See, critiques are only used till you learn. See, teachers are only, my teacher always used to say this. This is something that I keep quoting everywhere. He used to tell me that a good teacher is one who becomes redundant after some time, right. So, what is the definition of a good teacher is that after a while you should not see the need for a teacher. The point is you become independent. I mean, that is what good parenting is also about, all about, right. You make your dependents so independent that they do not have to come to you. So, this critique is a good critique if it has helped you to end up in the actual distribution, so that during inference you do not have to use it anymore. You discard the discriminator or the critique completely, sample from the arbitrary random variable, pass it to the generator, and what you get are the samples from the underlying distribution. That is the idea. Okay. You will be asked to implement this in your third assignment on the data set that we have given, and it's fun to do that. This is GAN. So, next class we will look at two other class of generative models. One is the variational autoencoders, and then the autoregressive models, also called as large language models. Okay. Thank you.